Hey everyone. So we're going to continue our study of Galois theory, and just to kind of keep our heads straight, what we're trying to do, right? We are looking at subgroups of the automorphism group of some field L, and we're trying to get the we're trying to establish connections between certain extensions, right, and certain groups, right? So there's this connection in Galois theory between groups and field extensions, right? And so we're sort of exploring what those interconnections are right now. And so our next theorem, of course, last time, our last lecture, involved the proof of theorem 5.3, right? So yeah, now we're on 5.4. That one was sort of not as that really didn't have a whole lot to do with Galois theory. That was just linear algebra. But now we're in a position where we're going to apply that theorem from last time into a theorem that involves groups and field extensions. So let's let G be, in this case what I want to be is a finite subgroup of the automorphism group of L. So let G in here be finite. And that's the only assumption we have here. So then three parts to this, three things are true. The first one is that the order of G is exactly equal to the degree of the extension L over phi of G. Okay. Part B is that G is equal to gamma phi of G. Remember, I think it was theorem 5.1, A or B, one of those two, gave us a subset. So we know that it's a subset in all cases. And now with this sort of small restriction, well, now we're going to look at groups. And if it's a finite group, then we actually get equality. And then the last part is that the extension L over phi of G is a Galois extension. So this is Galois. Okay, so for the proof, part A is really kind of the hard part, and then the other parts are a little easier. And it's not really hard, but it takes a little bit of, it takes some linear algebra, right? Because what we have right here, right, this is a statement about a basis for a particular vector space, right? And so I'm going to call that basis B. So let's let capital B be a basis for L over the fixed field of G. Now, by theorem 5.3, the set T of beta, where beta runs through all of capital B, is linearly independent with respect to either L or phi of G. And in this case, we want to use L. So this is an L linearly independent subset of, right, remember this is the set of all functions, the vector space of all functions from G to L. Thus, if we look at the degree of the extension, so this would be L over phi of G. Of course, that's exactly equal to the number of elements in B. And then this has to be less than or equal to the dimension with respect to L of L raised to the G. Why is that? Well, because we've got a linearly independent subset, so this subset has to have at most, or let's say, I don't want to say this, the dimension is a bound on the number of linearly independent elements in a set. So now, right, I said that sort of weird. If you have a set and it's linearly independent, it cannot have more elements than the dimension of your vector space. That's what I'm saying. So now, for each little g in capital G, define chi sub g, and this will be going from G into L, and it's defined by, so this is just the characteristic function. If you've taken, well, probably linear algebra you saw it, or maybe real analysis, you've seen this thing called the characteristic function. So chi sub g of h equals, it'll equal 1 if h equals g, and it'll equal 0 if h is not equal to g. Not equal to g. Now, so it turns out, let's say claim, so let's write it out. So if, remember, g is finite, so if g, capital G, equals g1 up through g sub n, then the set of corresponding characteristic functions is a basis for L to the G. So then the set of all chi G I, 1 less than or equal to I less than or equal to n, is a basis for L raised to the G. And so we'll just do a quick proof of this claim. So it's sort of a sub-proof, a proof within the proof. So, okay, so I need to show that it's linearly independent first. So if, and you know what, I should be very careful here. So this is over L. So proof, if alpha 1 chi g1 plus dot 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 plus alpha n chi sub gn equals 0, then what does that mean? Well, it means, so then alpha I, which is equal to this whole thing, alpha 1 chi g1 plus dot 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 plus alpha n chi gn of g sub I equals 0. Right? It's the 0 mapping. If you apply it to g sub I, you get 0. But if you apply it to g sub I, you get this. You get alpha I. And so what does that tell us then? It tells us that this is a trivial linear combination. So therefore, this set, I wish I could give it a name. Oh, it's all right. Chi sub gi, 1 less than or equal to I less than or equal to n, is linearly independent. Okay, so now we need to show that it's a spanning set, so I need to pick a function in L sub g. So now let's let little f be in L to the g. So now letting, say, epsilon I, this is going to equal f of g sub I, and of course that's an element of L. We have f is equal to epsilon 1 chi g1 plus plus epsilon n chi gn. Therefore, our set of chi sub g's spans L upper G. So that's the end of the claim. So claim done. All right. So now right, so now we have the degree of our extension L over 5G is going to be less than or equal to the dimension of, so that'll be the dimension of L upper G, which we just showed is equal to, right, the order of G. All right, the basis that we found here had exactly the same number of elements. We had there's a one-to-one pairing between the elements of G and that basis that we had for L sub G, right? These characteristic functions. So also, so we'll say on the other hand, and this is say theorem. Well, okay, let's write it like this. We know that G is contained in gamma phi of G. Gamma phi of G, which is equal to gamma of, capital gamma of, L over 5G. And so, this, and by the way, this containment right here, so this is by theorem 5.1, I think it's part A or part B, part A. And so, what does that tell us? It tells us the order of G is less than or equal to the order of this group right here. So, order of G less than or equal to order of gamma L over phi of G. Now, each element of gamma of L over 5G. What are those elements? Who are those things? Well, right, okay, so they are automorphisms of L that fix 5G. And so you can view it, here's a way to say it. So each element is an extension of the inclusion from 5G into L. Now, by theorem, this is theorem 4.3, so by theorem 4.3, there are at most the degree of the extension such extensions. So at most degree of L over phi of G such extensions. So what that's saying is that the size of this group is less than or equal to this number right here. So we can say, therefore, thus, so let's see, we've got order of G is less than or equal to this one right here, so order of gamma L over phi of G, which we know is less than or equal to this. Which we know, what do we know? Is less than or equal to G. Right. Which is less than or equal to G, order of G. And so, therefore, we get equality. So G, order of G is equal to the degree, right? It forces everything to be equal here. So degree of the extension. Okay, so that completes the proof of part A. Now for part B, by theorem 5.1a still, we have that G is contained in phi gamma of G. Right? But from above, we have, so it's going to be that the order of G is equal to well, all of this stuff. So which one do I want to do first? Degree L, degree of L over phi of G, which is equal to the degree or the order of the Galois group, L over phi of G, which, just switching notation, this is gamma phi of G. And so now we have a finite group contained inside a finite. So in fact, this is just set theory, right? Finite contained in finite, but they have equal sizes. So they, oh, and I should put bars around that. They have equal size. So finite set inside a finite set, they have the same size. They have to be equal. So there's where we use finiteness. Right, so since G is finite, we have that order of G has to equal the order gamma phi of G. Okay, now the last part, and this goes back, so this is from theorem, it's 4.8. The extension L over K is Galois if and only if there are exactly degree L over K extensions, or let's say this differently, L over K automorphisms of capital L that fix capital K. So now, if we combine parts A and B, so here we go. Let me. So combining A and B above, here's what we get. So it's going to look like this: L, a degree of L over 5G equals the order of G. This is what we showed in part A. And then that's equal to the order of gamma phi of G. This equality is what we proved in part B. And then this is gamma of L over phi of G. And this is precisely the number of automorphisms of L that fix phi of G. And so since we have equality, we can conclude that L over phi of G is Galois. So this right here, this is number of automorphisms of L that fix phi of G. So now we can just apply this, we can apply theorem 4.8 right here, letting K equal phi of G. So yeah, so that's it. Okay, and then I want to prove one more result for today. So this will be theorem 5.5. Once again, we just need a finite extension. So let's let L over K be finite. Two parts. So if L over K is Galois, then two things are true. First of all, the order of the Galois group of the extension is exactly equal to the degree L over K, and K is equal to phi gamma of K. And then there's sort of the counterpart here where if it's not Galois, so if L over K is not Galois, then the degree, or sorry, the order of the Galois group is strictly less than the degree of the extension, and we get proper containment. So, and say this K is a proper subfield of phi gamma. Okay. Proof. So we're going to just use the obvious thing. This is our theorem 4.8 that we were just referring to. So by theorem 4.8, L over K is Galois if and only if the number of automorphisms of L that fix K equals the degree of the extension. So if and only if the group of automorphism of L that fix K, it has order degree L over K, and otherwise it's strictly smaller. So, and otherwise is strictly less than the degree of L over K. All right, so we've seen this. The degree provides a bound on the number of extensions of the identity map or the inclusion map from K into L. All right, so this takes care of the first part of both A and B, right? It takes care of both of these. So this proves the first part of A and B. Okay, so now for the second part. So I think it's by just our previous theorem, right? Which is, let me say a little bit, whoops, before I actually say that. So since we're working with finite degree, we know that gamma of L over K is a finite subgroup of OT L. So this is a finite subgroup of OT L. So now, by theorem 5.4, I guess it's part A. Gamma of L over K, or the order of that group, that's equal to the degree of L over phi of gamma of L over K, which is exactly equal to L over phi gamma of K. Now, in the case that it's Galois, so if L over K is Galois, then the degree of the extension is equal to let's write this down first. The order of the Galois group, and that's equal to right, okay, and then this is equal to the degree of L over, make sure I get this right, degree of L over phi gamma K. Phi gamma K. Okay, now what we know, so since, right, we know that K is contained in phi, phi gamma of K, And so now what do we have? We've got two vector spaces here. We've got L with a couple of subspaces, or sorry, they give it, how do I say this? The degrees of these extensions are equal, and we have K sitting inside, and who is this? Right, so this forces us, so since this, we conclude that K has to equal phi gamma K, right? So because we have containment here and equality here, right? If this was a proper subset, the Tower law would make this fail, right? This equality could not happen. And so because of equality here, combined with containment, that forces equality right here. Now, if these were not equal, all right, so in the case, so let's say in the case that L over K is not Galois, then it's going to look like this. So now we have L over K is strictly greater than the order of the Galois group, which is phi gamma K. So what does that tell us then? That tells us that we cannot have these equal to each other. It tells us we have to have proper containment. We say, and so K is contained but not equal to phi gamma of capital K. Okay, so that completes the proof, and that's enough for today, so we will see you next time. Yeah.